So, welcome to this new lecture. As promised last time, we're going to be talking now about integrals of active value functions of a one-dimensional parameter. Remember that last time we talked about functions mapping real numbers or subsets thereof to vectors in a vector space. And we defined derivatives for those. We proved the mean value inequality for those. Now we're going to be talking about integrals and the relationship between integrals and derivatives, which is a kind of fundamental theorem of calculus. So when you want to make sense of this thing, this is equality over here. Okay, but first we have to go slowly and define integrals. So one of the main results today will be to show that all continuous functions are Riemann integrable, even if they take values in a vector space. But okay, let's start slowly, right? So we have some preliminaries here. I is going to be a compact interval of the real line. W is a Banach space with its norm. We have the set of continuous functions from I to W. We know that this set is a vector space with an appropriate norm that we saw in some previous lecture. And we also know that C, right? C is always going to be C from I to W with this norm as a Banach space. We also know that because the domain I is compact, all continuous functions from I to W are uniformly continuous, meaning, and there are different ways of stating that. Here I'm going to use this version where this quantity here, M sub f of delta, appears. This is the so-called modulus of continuity of f. So what is that? That's just the supremum of the distance between f of t and f of s when over all s and t in the domain, of course, with distance at most delta from one another. So I take all t and s with distance at most delta. I compute the norm of f of t minus f of s. The sup of that is by definition the modulus of continuity of f evaluated at delta. And uniform continuity simply means that this quantity goes to zero as delta goes to zero. That is, for any epsilon, there is a delta that makes the modulus of continuity less than or equal to epsilon. And of course, that definition we know. So that's just another way of stating that same definition, which is going to be useful for some of our quantitative estimates today. Okay, so we're going to be sticking with this notation for the remainder of this lecture. Now let's go back to one variable calculus. These definitions should ring a bell. So here I'm defining, you remember that for one-dimensional integrals, we define first Riemann sums, which are like approximations of a function f, or approximation of the integral of f. And the Riemann integral is a limit of Riemann sums. So what is a Riemann sum? Okay, first you have to subdivide this interval over which you're going to integrate x to y. There's a subinterval of a b. We're going to subdivide it into several pieces. So we're just going to place points inside this interval. The first of those is x. The last of those is y. And then we place these points t1, t2, up to tkp, right, in this interval. Only t0 and tkp are fixed. All the others we can choose at will. Besides choosing these points, which sort of divide the interval from x to y, we're going to choose inside each one of the subintervals a point SIP. So this construction of choosing the points t and then choosing the s's inside the corresponding intervals is called the marked partition of P. A partition has a size associated with it, which is this quantity here, this modulus of P, which is just the size of the largest interval that appears in this partition, right? As you break x, y down into subintervals, the size of P, the size of the largest interval that shows up in the subdivision. And the Riemann sum corresponding to the subdivision is this quantity here. It's the sum where you compute f at that point s sub I for each I, and you multiply the result by the length of the corresponding interval. For each s sub I compute the length of the interval from ti minus 1 to ti, or s sub I is contained, and I get this Riemann sum. Of course, for 1D calculus, we know this looks like this, right? So here I have my partition. So I have x, and y, which are the endpoints we're going to integrate f. And here are the points of the partition, so t0, t1p, t2p, t3p. Those are the t's, right? t4p is the last one. And then we have the marks, the s's, right? So s1p, s2p, s3p. Let me write this down. s3p, s4p. And you can see in the graph what we're doing, right? So basically, the Riemann sum is the approximation you get for the integral. We haven't defined the integral yet, of course, but we know it from calculus. So the Riemann sum is the approximation you get for the integral just by, instead of computing the integral over each one of these intervals, which is an area, you replace it with the area of this rectangle, and then this rectangle, and then this rectangle. This rectangle, of course, this is a signed area because if f happens to take negative values, then we get the negative of the area. But remember, we're considering f taking values over in a vector space W. So it's hard to perhaps visualize what this is doing, but it's something similar to this. I'm just approximating f as it was piecewise constant. There is constant over each one of these intervals with a value given by these points as sub 1, as sub 2, and so on. And I compute the Riemann sum is in some sense a generalization of this, even if f has vector values. Okay? So good. What is a Riemann integrable function? Here's our definition. A function is Riemann integrable over xy if, no matter which sequence of partitions you take, here see I made a little mistake, no matter which sequence of partitions you take, when you look, right? So as long as the size of the partition goes to 0 when n goes to infinity, right? So here we have our sequence. We're assuming that the size of the partition goes to 0, so the intervals are shrinking. And then what we want to happen is that the Riemann sums converge to something, which is this S of f. And this something, S of f, should be independent of the specific sequence of marked partitions that you take. So if I choose P sub n, the size of P sub n goes to 0. Then SF P sub n goes to SF. And if I choose another sequence of partitions with sizes going to 0, then the Riemann sum still converges to the same thing, this S of f here. If it is the case that this S of f exists, this limit that's independent of the sequence of partitions, we call this limit the integral of f from x to y. And this is how we represent it, right? Now, of course, I can write this down as this is the S of f above. This is a limit over any sequence of partitions with size going to 0 of the Riemann sum. Okay. Basic properties of this. So first one is the linearity, right? So if I take f and g, they're both Riemann integrable, and I compute lambda f plus g for a scalar lambda, I argue that lambda f plus g is Riemann integrable, and its integral, right, which is over here, is a linear combination of the integrals of f and g, well, with the right coefficient, right, the same lambda here. Why is this true? Well, I mean, first you check it for the Riemann sums, right? And many proofs of this subject are like this. So for Riemann sums, you just write the sums in full, right? So, well, you just go back to the definition. What would this look like if I had lambda f plus g as sub I here? Well, by just using the derivative, or right, by multiplying these vectors by scalars, I just use associativity, multiplicativity. You can easily get that the Riemann sum satisfies this linearity property. Now, this works for any partition P. Now, if I let P equal P sub n, and the size of P sub n goes to 0 as n goes to infinity, on the right-hand side, this converges to the integral of f, and this to the integral of g. Therefore, the left-hand side must also converge, right? So now I'm taking P sub n. And clearly, because the limits on the right-hand side are independent of the specific sequence of partitions that I take, the same must be true for the left-hand side. and then in the limit I get this linearity property. So, I mean, to sum up this proof, you just notice that Riemann sums are linear in the function you choose, and therefore so are the limits when they exist. Okay, so we proved this in some degree of detail. Here are two other properties that I'm going to leave as exercises. I mean, they're not difficult, but they require a little bit of thought. So first one is this proposition 2 over here. What it says is that if f is Riemann integrable from x to y and from y to z, then it's also Riemann integral from x to z, and the integral from x to z is the sum of the integrals from x to y and from y to z, except that we need to assume that f is bounded. Actually, I mean, you can show that if f is unbounded, then f is not Riemann integrable. So in some sense, there's a redundant condition. But just say, well, if f is bounded and Riemann integrable, then prove this. I mean, this is just a matter of looking at the Riemann sums of this guy, right, the partitions that give rise to them, and trying to write that down as a sum of Riemann sums over the interval x and y and z. Maybe you get a little remainder term, but you can argue that that hardly matters. So that's proposition 2. And proposition 3 is an estimate for the integral of f from x to y. I claim that this integral is at most the sup of f over the interval I, right, which contains x and y, times the length of the interval. So here's the sup, here's the length. So again, this comes from the Riemann sums. You just write the Riemann sum, try to bound it in the most stupid way, and this comes out. So it's a bound for all Riemann sums, therefore it's a bound for the limit. But as I said, I'm not going to do these exercises. You should do them. Okay? Good. Now we're going to talk about something more substantial, which is something we know about functions with real values, and are going to extend to functions with vector values, which is that all continuous functions are Riemann integrable. Well, I mean Riemann integrable over x and y for any x and y contained in the interval I, which I recall is a, b. So, I mean, a function in principle may or may not be Riemann integrable. It can be a pretty difficult problem to determine what is Riemann integrable or not. I mean, there's a Riemann-Lebesgue theorem for functions of one variable that tells us when a function is Riemann integrable, but it's a very substantial theorem. And now, what I want to argue is something simpler, that if you assume that f is continuous, then the Riemann integral exists. There is a limit to Riemann sums for any sequence of partitions with size going to 0, and this limit does not depend on the sequence you chose. Okay, but for this we're going to need a fact that it's usually proven, well, in a calculus class or in analysis over the real line, which is about these partitions, right? So it should be clear that at some point, well, we need to prove that there is a limit to the Riemann sums, and the limit doesn't depend on the sequence of partitions. So one of the key steps in the proof is to be able to compare Riemann sums for different partitions, right? So we have these two partitions here, P and Q, and we need to do something with them to compare the Riemann sums over Q and P. Here's the fact that we're going to use. That we're not going to prove it because it's usually proven in courses in either calculus or analysis over the real line, is that there is another marked partition called R, such that all these points T appearing in P are also points of R. And similarly for Q. And right, so I'm saying that, okay, if I want to find the points T sub I P in the partition R, I can do it. That's what is being said. Now, what does that mean? Right? So let me give a picture for the proof. So let me draw the points of the partition P in red, right? So the T's of the partition. So I have T0P, T1P, T2P, T3P, T4P, T5P, and this is T6P. And of course, they're the marks, right? So let me draw these as little dots over here. This is S1P, S2P, S3P, S4P, S5P, S6P. Okay, this is one partition. Let me draw another partition with a different number of points. That's going to be Q. So I'm going to write these guys on top. So the first point is, of course, the same for any partition. T1Q, T2Q, T3Q, and yeah, T4Q. That's the last point, and then there are the marks, right? So the mark S1Q is a point in this interval from T0Q to T1Q. Point S2Q is a point in the second interval. Point S3Q is a point in the third interval. S4Q is a point in the fourth interval. So again, this is Q, this is R, and what is, sorry, this is P. And what is partition R? Well, it's actually quite simple. You just basically, the T's of partition R are going to be the union of the T's of the two partitions. So this would be the first point for R. This is the second point for R. This is the second T for the third. Right? This is the second T for one of the two partitions being Q. So this is the fourth. Right? This is this guy here. This guy here. This guy here. All these two are the same. So the fifth point is this guy, T2Q. Yeah, the sixth guy is this one. Seventh, this one. Eighth, this one. And the ninth is this one. And the 10th is the same. So if you want, you can write the T's of partition R as T0R. What's the next guy? So it's T1P, then T1Q, then T2P, and so on, right? So this is the first, second, third, fourth, fifth, now is T2Q, and you can continue if you like. Right, so this would be the fifth, this is the sixth, seventh, eighth, ninth. The last one is always Y. So these are the points of R. Of course, I need markings for R as well. But that's simple. I just take anything that I like, and each one of these intervals will be a right mark. I'm not going to do it, but the important thing is that you understand where the points, right, the T points of R, the subdivision that R produces in the interval from X to Y, that they come from the union of the points of P and Q. Okay? And that's what we call a common refinement of P and Q. Meaning R is a refinement of P because it makes a smaller subdivision of the interval xy than P does. So basically R is obtained from P by adding more points to the subdivision, and the same for Q. And okay, how are we going to use this? We're going to use this to prove a fundamental lemma in the proof, which is this lemma we have on the screen right now. This lemma, let me remind you that this MF delta is simply the modulus of continuity. So sup of f of t minus f of s. Remember that f is vector valued, and t s belong to the domain, difference less than delta, less than or equal to delta. And what we're going to argue is this. take two marked partitions P and Q, and suppose that their sizes are both bounded by delta, where the maximum of them is equal to this delta here. So presumably, I'm interested in the case where delta is small. Both partitions have very small sizes. Now, the difference between the Riemann sums is also going to be small. It's at most 2 times the length of the interval times this modulus of continuity. Now remember, the modulus of continuity, because f, right, if I have an f that's continuous, the modulus of continuity goes to 0 when delta goes to 0 for all f continuous. So if delta is small, meaning if the two partitions have very small sizes, this difference between the Riemann sums and P and Q is going to be small as well. How do we make this precise? Right? I mean, we're actually going to show that this lemma is enough to prove the theorem. And how do we do it? Okay. First, let's show that if I take a sequence of marked partitions with size going to 0, then if I look, given epsilon greater than 0, let me take delta greater than 0 such that the size mf of delta is less than or equal to epsilon, and let me take it in not n such that let me actually be here a little bit more specific. So epsilon divided by 2y minus x, we'll see why, and take now an n naught such that for all n greater than naught, the size of p sub n is less than delta. Then what we have is that if I compare s of f p sub n minus s of f of p sub m, this is going to be less than, well, if both n and m are greater than n naught, this is less than 2mf, this delta that I just chose here. Let me call it delta tilde just to make it clear. mf delta tilde y minus x, and this is less than epsilon. So what we have accomplished is this. So we've shown that if you give me an epsilon positive, I can find an n naught such that if I look at all points in my sequence after an n naught, so actually this should be m and n greater than n naught, the corresponding Riemann sums are close together. They're a distance epsilon from one another. And what does this mean? It means that this SFPN sequence contained the space W, right? These are sums of vectors, they're vectors. And this sequence is, less than epsilon. This guy here is Cauchy, meaning the difference between the Riemann sum for P sub n and P sub m gets smaller and smaller as both n and m grow. So again, I'm using, right? So I'm assuming here that f belongs to C, and therefore it's uniformly continuous. The modulus of continuity goes to 0, therefore it's less than epsilon for a certain delta tilde that I chose over here. So if f is continuous, and we apply the previous lemma, we can show that SF P sub n is a Cauchy sequence for any sequence of partitions with sizes going to 0. And therefore, SF P sub n converges to something. But that's not all I need. I also need to show that this something does not depend on the sequence I picked, but that I can do by looking at these same estimates. Take two sequences of partitions. Right, one of the sequences is the sequence I had before. So I have that FP sub n converges to a certain S of f, and SFQ sub n minus SFP sub n is less than twice the modulus of continuity of f computed at size of, the maximum size times y minus x. And now, okay, the handwriting is a bit terrible here, but hopefully it's clear what I mean. So given that the size of p is going to 0, the size of q is going to 0, so this guy is going to 0, this maximum. And then the modulus of continuity is also going to 0, so this larger thing is going to 0. And therefore, the distance between the Riemann sums for q sub n and p sub n is shrinking to 0. Now, we know this guy converges to S of f. So it's easy to deduce from this that S f q sub n converges to the same limit. I just write, well, the distance between Riemann sum for q sub n and SF is at most the distance between Riemann sum for p sub n and SF plus the distance between Riemann sums for q sub n and p sub n. And this shows that the distance goes to 0. Okay? So if we have this lemma, then we can prove for any sequence of partitions that S, F, P sub n, the Riemann sums for P sub n, form a Cauchy sequence, and therefore they converge, right? We're assuming that W is Banach, therefore complete. So, and not only that, we can show that the limit doesn't depend on the sequence of partitions, meaning that it now compare this limit to what I get from another sequence, Q sub n. In the limit, it's all the same. So the lemma implies that F continuous must be Riemann integrable, right? And the question now is how we prove the lemma. Let's remember what the lemma says, just clear things up a little bit. We want to argue that this is true. Once we do that, as I notice, the theorem will have been proven. But now, what's the key step? The key step is that we're not going to try to compare the Riemann sums for P and Q directly. That would be very complicated. What we're going to do is you're going to compare P and Q to the common refinement R. So the proof will be to compare each one of P and Q to the common refinement R. So I'm going to show only the following inequality. Riemann sum Fp minus Riemann sum Fr. I'm going to show that this is less than 2mFp given y minus x. And once I show that, I have, of course, the same thing for Q. And then the distance between Riemann sum for P and Riemann sum for Q is at, there's no 2 here. I'm going to prove this. And if I have that for P, I also have it for Q. And then I can just add up the two bounds to get a bound on the distance between SFP and SFQ. Okay, but how do we do that? Okay, the idea is to use the refinement property, right? So let me very quickly write down the point of P, or draw them, right? So this is sort of random. I mean, the picture shouldn't be trusted too much, but hopefully it'll make sense, at least give an intuition for how we prove this. And then the formal argument's a bit annoying to write, but not too annoying. So this is P, right? These are the points of P. And of course, to compute the Riemann sum, I'm going to add up a piece that's like the length of this interval times f at a marking, plus the length of this interval times f at a marking, and so on and so forth. The Riemann sum for R is a little bit different, right? So we know that the points of R, they contain these red dots that I drew, these red stars, right? The points of R, there are more points in R than in Q. So the points of R include those of Q, and also there are also a few more. So maybe I should draw this as these are stars as well. So, okay, how are we going to use this information, right? So basically, here's what we're going to do. So in the Riemann sum for R, I have a sum over this interval, there's a guy here missing, this interval. And what I'm going to do is this. I'm going to compare these two terms in the sum for R together with this single term in the sum for P. And then I'm going to move on to the next point of P, and I'm going to bundle up all these terms for the Riemann sum of R and compare it to the single term in the Riemann sum for P. And I'll keep doing this. Right? So these guys I compare to the sum of these two. These guys I compare to this guy, right? So I compare to these two, and so on and so forth. And we're going to show that this difference is small. Well, I mean, it's small in the sense that it can be bounded by the modulus of continuity. How do we do that? So we need some algebra, right? So again, let me write, I'm going to call these points of R j equals 0 to the k of R, points of R, and I'm going to look at these indices. Well, y0 equal to 0, less or equal to I1, I2, up to I of k of P, which is equal to k of R, such that the ith point in partition P is equal, let me call these J's, okay? Because I have J above. So the ith point in P is equal to the J-ith point in R. Okay. So as I said, the algebra is maybe a bit confusing, but the idea is that we're going to use these guys to do this bundling process that we described above. Right? And I mean, how do I know that these J sub i's exist? Well, that comes from the condition that R is a refinement of P, that I can find all points of P within the points of R. And I'm just doing it in a way that I match, well, the first point of P to the first point of R, the last point of P to the last point of R, and so on and so forth. Okay, so now let's write the Riemann sums for these two partitions, okay? So I'm going to write the Riemann sum first for P. So this is a sum from I equals 1 to k sub P of T I P minus Ti minus 1 B F S I P. And because I want to help make myself more comfortable, I'm just going to write this in terms of these J sub i's that I just defined, right? So this is Tj sub I of P minus Tj of I minus 1 of P F S I P. And I'm going to replace this again by something else. I'm going to do the sum of I equals 1 to k sub P. Right, so, this should be Tji of R, Tji minus 1 of R, right? So these guys are equal here. And now I'm going to do something slightly different. I'm just going to take sum from I, and then sum from j equal to ji minus 1 plus 1 to ji tj minus tj minus 1. Sorry about that. Now what did I do from here to here? This is just a telescopic sum, right? So it should be easy to compare the two, right? So I add these guys here, this tjr minus tj minus 1r. As I add them up, there are lots of cancellations, and I'm left with the last term, which is ji, and the first term, which is, well, the first term would be ji minus 1 plus 1, but I have this j minus 1. So it's going to be, right, ji here and ji minus 1 here. So, okay, these two things are equal. Why is this convenient? Because I can write down the sum of the partition R, the Riemann sum, in a similar fashion. And so let me actually, if you believe what I just did, I'm just going to say, okay, let's erase this, and let's keep this kind of this convoluted way of writing the Riemann sum of P as our for future use. And I'm going to delete this, sorry. I'm going to now copy this one to the top. And maybe I need to do this, and now I'm done. Yeah. And now I'm going to write down the Riemann sum for R. And maybe now will become clear why I did what I did above. The reason is that by doing what I did above, I've managed to, these TJRs, TJ minus 1Rs, are precisely the guys that appear in the Riemann sum for R, which is precisely the thing that I'm writing right now. And now, to make these things more comparable, I'm just going to say, sorry, this is KR. I'm just going to say, okay, let's break the sum up into parts, and that's the bundling that I described before, right? So first, I'm going to consider, right, if I take these intervals in the R partition, I compare them to the P partition, and I match. So I'm going to take J from J, I minus 1 plus 1, J sub I, TJR minus TJ minus 1R, FSJR. And notice that now I know how to compare the two things, right? Well, first of all, why is the sum at the bottom equal to the sum at the top, right? So why is this sum equal to this sum? Well, it's just a matter of keeping up with the indices, right? So here I have a sum, and I go from index ji minus 1 plus 1 to ji. And if I look at this double sum here, contains exactly the terms that appear above. Maybe you need to think about it a little bit, but it's just a way of partitioning the terms of the sum above. So, okay. In any case, I want to keep these formula, and like I did before, I'm just going to keep the formula that's the most convenient for me. And I'm just even going to make my life even simpler by doing this. Now I'm going to compare the two guys, and I've set myself up in a way that's the most comfortable for this comparison. Of course, I can move this aside and this aside. So I'm just going to look at these differences. And I'm going to compute the norm of that eventually. Now, here will come the key step in the proof. So when I look at the difference, I have, the sums have the same indices, and they're the same TJs and TJ minus 1s appearing here and there. And therefore, I'm just going to say, well, the difference is the sum TJ minus TJ minus 1 R. And notice, well, this is a vector, and this is a scalar. So maybe I should reverse the order, but who cares, right? Now comes the key step, okay? So let's see what we have right now. So look at a fixed index J here that belongs to one, J, fixed I, fixed J. So here I have Ti minus 1 P, and this is Ti P. Of course, okay, sorry, let me use the space at the bottom. Okay, let me do it like this. So I'm gonna do this comparison, like this. So I'll use the sum eventually, right? So, but I need this thing first. So take this guy and this guy. What do we have? We have here ti minus 1p, tip, right? I'm fixing I and then a j between ji minus 1 plus 1 and ji, and then comparing the corresponding terms. Of course, the coefficients here are exactly equal, but these guys are not, right? So here I have 2 points of the partition P, and their main import for me is that if these are the same points that I call tji minus 1 the partition R, and tjir. So the difference between partition P and R is that R potentially has more points inside. Right, so the size of this interval is less than the size of P, right? Because what is the size of P? Is the maximum spacing between T sub I and T sub I minus 1 as I run through the indices of partition P, run through the points of partition P. Okay, but now I'm not computing f at any one of these points that I drew already. I'm computing them at potentially different points. So let's say that SIP is a point in here, and SJ, well, maybe this is J, maybe this is TJR, TJ minus 1 R, and here I have the corresponding marking as R. The observation, which you can make precise, is that both SJR, and SIP, they belong to this interval from Ti minus 1p TIP, and therefore their distance, right, again, remember I'm fixing indices above, and I'm comparing the corresponding SJR and SIP at the bottom. And I'll just argue that, well, the distance between these 2 points, they're both in the same interval, so the distance is at most the length of the interval, which is at most the size of P. So now I have my key step. Why? Because if I know that 2 guys are at a distance at most something, I know how to bound the difference. This is at most the modulus of continuity of f computed at the size of P. What is the modulus of continuity? It tells me the most that the value of f can change when I change the argument, the point where I'm computing it, by at most, well, delta, right? If this is delta, then I'm arguing that these guys are at most delta apart, and therefore the values of f are at most m sub f of delta apart. And now everything becomes clear, I hope, right? So I wrote the sums for P and R in a way that I could directly compare these intervals. So when I'm adding up over a small interval in the partition R, that small interval is contained in a larger interval in partition P. But the larger interval still has a size that's bounded by the size of P. And that means that the distance between the mark in partition P and the corresponding mark in partition R is not more than the size of P. And therefore the difference in values of f is not more than the modulus of continuity computed at the size of P. And if you agree with that, then now we can finish the bound. We can rewrite the sum as I did before. So let's compute a norm, right? And as usual, we're just going to bound the norm by subadditivity. So I'm just going to say, well, I have all these terms that exactly match one another except that the value of s changes. So let me say, well, the norm of the sums at most the sum of the norms. And then I have these scalars, right? So and the scalars come out, well, they're no negative. And then I have the difference between f of s sub I p minus f of s sub j r, which, as we saw, is bounded by the modulus of continuity. So we can just bound everything by the modulus of continuity, right? So computed at size of p, plus the sum of these points. And now you have to think a little bit about what the sum is. So remember that before I said, well, this sum that I wrote is just a funny way of writing a sum of all consecutive distances between points of the partition R. I mean, it happens that I wrote the sum with a double index, but as I argued before, that's just adding up all the little intervals in partition R. So the whole sum is a telescopic sum, and is exactly equal to the last point, which is y, minus the first point, which is x. So this is equal. And now I'm done, right? So because the norm of the difference between, the norm of the difference between Riemann sums is at most this modulus of continuity times the length of interval y minus x, which is exactly what I set out to prove over here. And that means that I can compare the Riemann sums of P and R, also of Q and R, and then if I combine the two, I have that key lemma that allows me to compare Riemann sums for any two partitions. And this is the end result. Sorry. Now, we argued before that the lemma implies this very important theorem, which is that all f that are continuous over I are Riemann integrable over any subinterval. So now we know that the integral of any f over I is well defined. Sorry, this is not I R, right? So this is I W. So now we know that the integral is well defined for any function from an interval of the real line to vector space. And we know we have these properties, right? That the integral from x to z is the integral from x to y and for y to z. So we're in very good shape. But there's still something that I want to do, which is this fundamental theorem of calculus. And what is the fundamental theorem of calculus? So define a function capital F as the integral of a continuous function small f. The theorem says that when I differentiate capital F, I get little f back. Right? I get, to say it again, the integral of the derivative of the integral of f, little f, is equal to little f. When I take the integral and then do the derivative, I get the integrand back. Okay, how do we prove this? So for this, it turns out to be convenient to have the following convention. So we defined the integral from x to y of f with t. Sorry, let me write f of s as above. Of course, this s inside the integral is just a dummy variable. We defined this for y greater than x. And now we're going to say that the integral from y to x is going to be equal to, well, that's what we do in calculus, for integral from minus x to y. So we know how to integrate both from one smaller point to a larger point, then the other way around. Just reverse the thing. And then we have this rule that is additivity rule for any 3 points in the interval I have that the integral from x to z of f of s d sub s equals the integral from x to y plus the integral, let me abuse notation a little bit, f of s d sub s. So I can decompose the integral into two parts, right? That's using one of those propositions that I left as an exercise. Again, I wrote here CYR, it should be CYW, right? Everything I'm doing about vector value functions, otherwise there's nothing to be proven. Okay. And Right, so how am I going to use this? Well, I defined this function capital F. First of all, is it well defined? Well, the answer is yes. And the reason is that little f is a continuous function. Therefore, I know that it's integrable, and the integral from a to any t inside the interval I is well defined. Okay, so let's work from that. And that's going to be our last step. So now I have this guess, right, that when I look at capital F of t plus h minus capital F of t divided by h, of course I have to be careful that when I do this, t plus h is always contained in the interval I. I'm going to omit any consideration of that. I'm just going to say that, well, this is, I want h to be non-zero, but that should be fine too. And here I have minus f of t, and my suspicion is that as h gets smaller and smaller, this quotient here, right, the quotient that gives you the derivative of the limit, should get closer and closer to little f of t. So let's find a way to write this down with the integral, right? How do we do this? So I'm gonna, well, one term is easy, right? The term between brackets is just 1 over h. I just use this, right? So this is an integral from a to t. This is right? This guy is an integral from a to t. This is an integral from a to t plus h. So the difference is an integral from t to t plus h with this the convention that I've just adopted. Now, we know how to estimate integrals. Little f by itself is not an integral, but I can put it inside the integral because I'm integrating over s. So this is a trick that we play in calculus all the time, right? So here my variable of integration is s. So what happens if I integrate a constant, something that does not depend on s? Well, I get simply that constant times the length of the interval, which in this case is h, but I'm dividing by h. So the integral of this bit, f of t, which behaves like a constant in this case, this integral divided by h gives you back f of t. So this is good because now I have a single integral encompassing everything that I need to consider. And I'm going to use this fact that we saw before. Well, first I'm going to pull out the h out of the norm, and then I get the absolute value. But now I'm going to use this fact that we used before. We saw before that the value of an integral is at most the length of the interval times the integrand. Of course, we saw it for the definition of integral from x to y, where x is less than y. But the same thing works if I have x greater than y, as long as I take an absolute value of the length, right? So that formula is still valid if I use the length of the interval. What's the length of the interval in this case? Well, it's t minus h minus t, which is exactly h, times sup norm of f of s minus f of t. And the s has to be in the interval where I'm integrating. And let's see what this gives us. Well, okay, t plus h minus t is h, so this is going to cancel, right? So of course, let me just say it again, that h is positive. Okay? So, and here I have f computed, right? At this point here, I have f computed at 2 points. One of them is t, and the other one is at most a distance modulus of h away. Here, notice that I'm abusing notation. Maybe h is negative, and then this interval is not very well defined, but you know, you take it, the well-defined interval between t and t plus h, which might be the interval from t plus h to t, or from t to t plus h, depending on the sign of h. The important thing, however, is that the distance between s and t is always less than the modulus of h. So when I'm computing a function at 2 points, and the distance between them is a certain delta, this difference, right, the norm of the distance, is at most the modulus of continuity at delta. And my delta in this case is just modulus of h. So to recap, I started out from this difference here. The quotient that should give me the derivative minus what should be the derivative. I wrote this difference as a single integral. And now I bounded this integral by the, well, there's this factor that was pulled outside, there's the length of the interval, and then the sup of what's inside. And the sup of what's inside, I said, well, just f computed at 2 points whose distance is at most the modulus of age. So this is bounded by the modulus of continuity of f computed and modulus of age. Now, what happens when age goes to 0? When age goes to 0, remember that f is uniformly continuous. Simply because it's continuous, it has to be uniformly continuous. So the modulus of continuity, as we've seen several times, goes to 0. And what have we shown? Well, we have this norm here. Well, it's greater than 0, for sure greater or equal to 0. And it's sandwiched between this guy that's 0 and this other guy that goes to 0. Therefore, the norm goes to 0 when the modulus of h goes to infinity. The quotient that should give me the derivative in the limit indeed converges, and it converges to little f of t. And now we're done, right? Because what we wanted to prove is that the limit of the quotient was equal to little f of t, and that's what we've just accomplished. So this finishes the proof of our version of the fundamental theorem of calculus, which is this nice result here. I'm just going to finish with a quick remark which says the following, that if W, the space where f takes values, is R to the k, then, okay, the integral is always a vector, right? That's by definition, because it's a limit of Riemann sums, and Riemann sums are vectors, so this is a vector. Well, so this is a vector in Rk. And if you look at the ith coordinate, that's just the standard integral, right? If you look at the ith coordinate of function f, and you integrate it, that's what you get. So if your function takes values in Rk, then this Riemann integral we defined is just defined coordinate by coordinate. And particularly if f is continuous, all coordinates are continuous, so we're in familiar territory. However, we're going to be, at some point, maybe discuss things that do not necessarily correspond to Rk. So it's going to be useful to have this more abstract notion. But okay, that's all I had to say this time, so thank you very much.